This is May, June 2023, paper 22. So you can go through the definitions from the marking scheme as well. I will not be taking time to explain them. So very simply, this is actually force per unit area. And it is believed that if you see in the marking scheme that the force is exerted in such a way. What is that way? So be that any surface area, for example, like this one, it is believed that the force is actually perpendicular to the surface. For example, if this was a curved area, like a gas cylinder that we sometimes have, then the force will be exerted in all directions like this, but believed so that it is actually acting at an angle of 90 degrees, even along the curved surfaces. Okay, momentarily for that point. So it says you want to show that the pressure has base area or the base units like this one. Simply go towards force divided by area. We have force from MA divided by area. We have m as kg, acceleration as s minus 2, and area is m2. This becomes kg, m minus 1, s minus 2 by bringing this in the numerator. Basic algebra, nothing too difficult. Then he tells you to figure this out, the units of the constant. Okay, no need to worry about this. He wants you to figure out the constant. Let's replace the constant in the correct position. So let's bring this k over here and m over here and ignore pi and 8 because they are constants. So what is the equation that we are left with? We are left with the k equals to delta p into r raised to power 4 into p into t divided by m into L. Now everything is defined over here, that density is this, r radius is this, so this radius r will have a unit of m, length will have a unit of m, density will have a unit of kg m minus 3, m is kg, and t is time seconds, and p is the pressure. So pressure was already found in the previous part, so we don't have to find it again. So this becomes kg m minus 1 s minus 2, because this is why he gives you this part, to show. If you're unable to show this, then at least you know what the pressure is going to be so that you can solve the next part. Let's replace everything in place of everything. So we have kg m minus 1 s minus 2 in place of this, then r4 will be m raised to power 4, then v, the density, which is kg m minus 3 into t, which is second s, divided by m is actually the mass, which is going to be kg, multiplied by L, which is the length L in meters. Okay, so once you are done cancelling each other out or cancelling these factors out, you will realize that the factor that you're left with is actually going to be kg m minus 1 s minus 1. So be careful about the cutting. This will be the answer. You can pause the video and try it on your own. So next he asks you which one is going to be the highest contributor in the percentage uncertainty. So the percentage uncertainty, if we go back to the formula, the comparison is between L and R. If we go back to the formula, we see that L has a power of 1, R has a power of 4. So it is going to be 4 times as more contribution, or you can say it is going to contribute to the error 4 times as much as L. So if they have an error of 2% each, for example, R has an error of 2%, L has an error of 2%, what is the total? What is the eventual error percentage? You see, due to the power rule, we see that R is raised to power 4. So this 2% multiplied by the power is equal to 8%. So R, in fact, is going to be 8% more, or it is going to contribute an error of 8% higher, or 8% in comparison to 2% of just L. So I've just explained the method, what he's going to explain to you in the marking scheme. You can write this answers. You can write this answer in your own English, in your own words. But since he says quantitatively, we have to show that where do we get this 8%, and what are we comparing it with? We're comparing it with 2%. Okay. Moving on to the next, again, check the definitions from the marking scheme. Very easy and very straightforward definitions. We're not going to waste our time into these definitions if you can memorize them. Moving on to the question, he says that the system is in equilibrium, right? All the measurements are given to you, and he wants you to find out the tension T in the string. First, if you see anything or a force at an angle, first make the components of it. Okay, so if you make a component over here, which is also acceptable, 60 degrees. This will become t cos of 60 degrees. If you make it over here, this will become t sine of 30. As I explained earlier, it does not matter. You can use both of them. It will not matter. Now he wants you to find out the tension T. So we're going to make the equation, but first let's visualize what's happening. So this is going to cause a rotation in this direction because of the pivot. This is going to cause rotation in this direction, and this is also causing rotation in this direction. So I have two factors on the right hand side which are working together, and only one factor on the left hand side trying to make sure that the rotation actually goes anti-clockwise. Let's make the equation right now, right here, so that we don't have to go back to this space. Okay, I'm writing the equation right now over here. So I have the moment formula is F into D. So the force is 54, the distance is 0.45 from the pivot, of course. So this will be 54 multiplied by 0.45. Along the pivot, we draw an equal to sign because this is where everything is happening. Okay. Next, we have this 2.4 mass. So 2.4 into 0.95, because that is how far this is from the center point of that cube. Second factor that is still left out is this 0.35 at this point. But since we take the distances from the pivot, be careful, we have to take this whole distance up to this point. So the t sine 30, which is this one, is actually 0.95 plus 0.35 meters away from the pivot. When you solve this eventually, of course, please do the algebra correctly. You can take this factor on the left hand side, subtract it from this point, and then divide it with this, then divide it with sine 30. Do it step by step, please. Okay. You'll find that the answer of tension T comes out as 33.87 newtons, but we write them in two significant figures as 34. Then we have the string is cut, so the beam is no longer in equilibrium. Okay, fine. Calculate the magnitude of resultant moment. Now see, you'll have to find out the resultant, or you have to find out the moment of everyone around the pivot. You see the 24 or the 2.4 Newton moment was approximately 2.28 Newton meters. The string and thread was generating approximately 44.2 Newton meters, and the mass on the other hand was generating 24.3 Newton meters. How we have found them? We have multiplied everyone's F into D separately and calculated these answers. Basically, this, and this have been calculated independently, separately again for this last part. He says the string has been cut. So the only thing trying to hold back this moment is 2.28. So the resultant moment will be 24.3 minus 2.28 because it is going to go clockwise. This is anti-clockwise. So in this tussle, in this the dominance is going to be for 24.3. We are left with 22 Newton meters. 22 Newton meters, right? Okay. This question is from Work Power Energy. He says that it already has a speed of 3.4 meters per second at this point. It is 1.8 meters high. The weight is already given to us. He says find the gravitational potential. So change in GPE will be equal to mgh simply. So be careful that mg is already given to you, which is 2.4. Okay. So this is 2.4, and the height above the Earth's surface is 1.8. So 1.8 equals to, if you calculate this, you're going to get 4.32 joules. So this is 4.32. Up to two significant figures, this will be 4.3. Second part is going to call for law of conservation of energy. He says use your answer to C1, which is 4.3, conservation of energy, to find out the kinetic energy at Y. Now we know that the ball, it was already moving with some kinetic energy. So 2.4 divided by 9.81 multiplied by 3.4 whole square. It's already moving at a certain kinetic energy. Let's call this as kinetic energy at X. And then gravitational potential energy was invested back into the object because it lost height to move from X to Y. Gravitational potential energy was invested, was given to this object, right? So apart from it already having kinetic energy, now it has gravitational potential energy. So kinetic energy at Y is equal to kinetic energy already, what it already had at X, plus the change in gravitational potential energy right now invested in it. So 1 over 2 into its weight divided by 9.81, because we want to convert this into kilograms, multiplied by the velocity square, which is 3.4 whole square, plus 4.3, which is going to be invested in this object in the shape of gravitational potential energy. Now, when you're done with this, when you solve this, you get 5.7 joules. So the kinetic energy is 5.7. Now, just to understand this, since you are adding energy into the system, I can suspect that the velocity at y will be higher than 3.4, because approximately 4.3 worth of gravitational potential energy was invested back into the system, was brought into the system. He says, what is the direction, if any, is the acceleration, and is it going to change? So there is no variation, because at all stages there is only one factor responsible for acceleration, and that is gravity. Gravity at this point, the gravity at this point, and of course gravity at this point. At all points the gravity is acting. So is there any change in acceleration? There is no change, right? And it is always vertically downwards. Now he says that draw the horizontal component. You see, if we go back to this diagram, the horizontal component is not being affected by anything. Although if this was a non-ideal case, then drag would be affecting this. But if this is an ideal case, we are ignoring the air resistance, is negligible. So the forward component, what it already had, will remain same, because in that horizontal direction, there is no resultant force acting which can bring about an acceleration and change the velocity. But in the vertical direction, we can see that the velocity would be increasing because of the gravitation. So right now, the horizontal component will have a non-zero value and will be a constant answer. But let's say if we had to draw this for a vertical component, what would have happened? So from Tx till Ty, we would have started with a velocity of 3.4 meters per second. For the sake of example, let's say. Otherwise, we would have had components that this 3.4 meter per second, which we are already given, how much of this is in the forward direction, how much of this is in the downward direction, according to the angle theta, of course, vector components. But we're ignoring that for now. And after some time, due to the gravitational acceleration, how much velocity it would have gained, that would have been a separate answer, right? So this is what the graph would look like if that would have happened. Okay, all right. Question number 3. So in question number 3, we have a question of momentum. Okay. So in momentum, he asks us that there is a resultant force, there's a resistive force backwards. Okay, fine. So from 0 to 3 seconds, we have a constant force of 1.4 newtons in the object, which is of course going to cause acceleration. Why? Because in this duration, 1.4 newton, the forward force is greater than the resistive force, which according to F equals to ma, 1.4 minus 0.8 equals to mass of the object, whatever that may be, into the acceleration. It will produce an acceleration. There will be a velocity. There will be a change in velocity. So if there is a change in velocity, there will be a change in momentum. Anyways, what is force? Again, rate of change of momentum. Please see the definition from marking scheme. Determine the change in momentum of the block from 0 to 3. Now, since we're expecting a change in momentum, we can go back to the formula, that is F equals to rate of change of momentum. Bring that to here. This is resultant force multiplied by the change in time multiplied by a change in momentum. Now, what is the resultant force? Now, coincidentally, what has happened is that the graph actually comes down to 0.8 again. So students sometimes misread this, or they develop a misconception that probably this is what's happening. No. What is the change in resultant force? You see, previously the resultant force, or the force, was 1.4. Now it reduces to 0.8, which is this one. And we know that if it is moving at 0.8 or has a force of 0.8, it will no longer experience a change in momentum, because forward force and backward force will be equal. The acceleration is 0. There is no change in velocity. So the change in force is from 1.4 newtons to 0.8 newtons. So I'm going to erase this. So force changes from 1.4 to 0.8 in a time frame of 3 seconds, right? So delta P. So delta P comes out as 1.8 kg per meter square, kg per meter second, kg meters per second. Okay. Describe and explain the motion of the block between time t equals to 3 and time t equals to 6. What's happening with the object when it actually is in this region? from 3 up to 6. What happens with it? Now, since the force comes down to 0.8 and the resistive force is also 0.8, there is no resultant force, which I've already discussed theoretically. So you can simply write down box moves at a constant speed. The resultant force is 0, right? Because on the block, the forward force is 0.8 newtons and the backward resistance is 0.8 newtons. It moves at a constant speed. He says that X produces a total power 2 watts moving from 3 to 6. Okay. A plausible situation. Why? Because when we apply the formula for power equals to force into velocity, we already understand that this is a constant force producing a constant velocity. There is no acceleration. So be that a forward force of 0.8 or consider this from the backward force perspective, it would not change. It would not matter. The answer will still be the same. So power of 2 watts have been developed or has been developed with a force of 0.8 newton. So what is the velocity that can be extracted out of it? So currently it is moving at a speed of 2.5 meters per second. They tell us what is the distance moved in this time frame. Now, since we have the speed, we have the time, we can use the formula speed equal to distance over time simply. Speed is 2.5. Time taken for the process is 3 seconds because we move from 6 to 3. So the difference is 3 seconds. So distance comes out as 7.5 meters by multiplying this. So we get 7.5 over here. Then we move to question number part C. In part C, we see that what will be the change in momentum. You see, from a 0 up to the certain point, the momentum was changing, right? Because there was a constant resultant force. There was a forward force of 1.4. There was a backward force of 0.8. A constant change of resultant force for producing the acceleration. The acceleration was producing a change in velocity, so the momentum, which was mass into velocity, was also changing. So it changes from 0 up to a value of 1.8, which we found in the previous part, which is this one. So he leaves a blank canvas for us. So let's put in the variable. So this is 1, this is 2. I'm going to choose the scale. So 1.0, 2.0. Up to 3 seconds, I realize it goes up to 1.8. So you can count the number of boxes from this point, and it goes up to 1.8, for example, somewhere along here. And 3 is somewhere along here. Excuse the drawing, you can count the number of boxes on your piece of paper as well. So we draw a straight line, and then after this time, we realize that the force comes down to 0.8. Now, the forward force and the backward force become equal. If they become equal, there is no acceleration. If there is no acceleration, there is no change in velocity. If there is no change in velocity, then there is no change in momentum. So it maintains that momentum till the end of time. Okay. All right. The next question is about Hooke's law, distance. Now, this graph is interesting. Please notice that we have a spring. What is the meaning of this coordinate? There is no force, but there is a length. Basically, this is what it means, that when the spring is hanging with no load, with no mass, at that time, the total length is 8 centimeters. So as you start putting in the weight, as you start putting in the load, the spring starts increasing its length. So if you had to find the extension, please be careful. You'll have to take the difference by visualizing them separately. Okay. All right. So he says the relationship, the name of the person. So Hooke's law. You can see the marking scheme. He says determine spring constant in newtons per meter. No problem. The gradient of the graph is actually the Newton, the spring constant, because we have F equals to K times X, and we know that K, or this is actually the change in length, equals to this. So K becomes equals to change in force that causes the change in length, L2 minus L1. Okay. All right. So, or you can open this up as F2 minus F1 divided by L2 minus L1. Simply put, what you can do is a force of 12 newtons has caused an extension from 8 centimeters to go up to 24 centimeters. The force increased from 0 to 12. The length increased from 8 to 24. So K is equal to 12 newtons divided by 24 minus 8 with a power of 10 to the power minus 2, because this is centimeters and we need our answer in newtons per meter. So K is equal to 12 divided by 24 minus 24 minus 8 with a factor of 10 to the minus 2. K comes out as 75 newtons per meter. If you don't convert the centimeters, then it will give you a different answer for power, but the digits will be the same. He says determine the elastic potential energy for F equal to 6. No problem. So when you go to F equal to 6, you have to go back to the graph. What is the change? What has been the change? So up to 6, we realize this is going to be the point. So we find that this is the area that we need to calculate. Okay. It starts at 8, finishes at 16, and goes up to 6. Simple triangle area. So 1 over 2 force into extension. So 1 over 2 force goes up to 6. X goes from 16 centimeters to 8 centimeters. And please be advised, of course, you'll have to include the 10 raised to power minus 2 factor over here. The answer will be 0.24 joules. So 0.24 joules were stored in the spring when this action was taken place. Okay, so question number 5. He says that what is the motion of the particles during a transverse wave? So in this, we are familiar that they are actually moving perpendicular. And in this, they are moving parallel or along the direction of the wave. If you're unsure about this, let me show you an animation for this. Now, in this, you can see that we are discussing a sound wave. This is how the particles are moving. You see, at any moment when you pause this, you will realize that there are few sections where the particles are very close to each other. This is a compression of the sound wave or longitudinal wave. And this is the rarefaction that we talk about when the particles are away from each other. So you can see at this region, the particles are under low pressure. In this region, the particles are at high pressure. And notice, this is the source from where the sound is being produced. And let's say this is the listener or the observer. How is the energy traveling? The energy is moving from the source up to the observer. Is that so? Right? So the direction of movement of energy is exactly the same how the particles are moving. Pick any particle, watch the animation again, and see whether the particle is moving forward and backward or not. This is why we say that in a longitudinal wave, the particles are moving in parallel. Let me clear this out and play the animation for you again. Okay, so notice how the particles are moving forward and backward, forward and backward, forward and backward in the direction of the movement of energy. Okay, coming back to this paper. So he tells you that there is a stationary wave that has a frequency of 1.7 that has a velocity of this much, and A is the antinode. So what is the wave produced in this tube? We know that this is a closed end, and closed ends experiences a node, and we know that the open ends experience an antinode, which is already given by the examiner. Okay, so if this is the antinode and this is the node, this is the expected shape of the stationary wave that's going to look like. And if this is the antinode again, so the expected shape of the wave is going to look like this. Okay, so this is how the wave is actually going. So how is, and you can say, if you want to discuss this further, if you want to understand this further, you can watch the video of stationary waves on my channel. So up to this point, we can see that this is actually lambda by 2. And from this point onward, this is lambda by 4. And the total length of the tube L is not given to us. He says, find out the wavelength. Okay. So previously, what we can do is simply use V equals to F lambda to find the wavelength. V is 340. Given to us over here, frequency is 1700 because it is 1.7 kilohertz. This is lambda. Lambda comes out as 0.20 meters. So this is 0.20 meters. Now he asks us what is the length of this. So we know that it is lambda by 4 plus lambda by 2 equals to the length L. This comes out as 0.75. Lambda equals to L, length L. Okay, so 0.75 multiplied by 0.2, which is this one, which we found already, is length L. So L comes out as 0.15 meters. Now this is going to remain fixed because the pipe cannot change physically. This is fixed, right? We can't do that. Okay. Moving on to the next question, he says the maximum wavelength of the sound wave produced from the speaker that can produce a stationary wave in the tube. So to find the maximum wavelength, It means that I want a very large wavelength, as large as possible. What could be the possibility to create a wavelength of a stationary wave in this scenario? So if I want to create a very large wavelength, the frequency should be minimum. It should be the smallest. And if you go back to my lesson, you will see that this is actually another way of asking about the fundamental frequency. Okay, so let's see. What can I do? I have a space of 0.15 meters. What is the smallest wavelength that I can squeeze here? So an antinode in the open and a node on the closed end. So this is the wave that I can make in the smallest possible configuration. So this is actually lambda by 4. So my lambda by 4 comes out as 0.15. Lambda comes out as 0.60 meters. So the smallest possible case I could have done is 0.60. You see, there is no limit to the maximum case. Why? Because we can keep on going into the next and next phase. It keeps on making like this, right? And so on and so forth. There will be no limit to that. So it's very natural to think about it in this way, that what was the smallest extreme? You see, this is the largest wavelength. You cannot make a stationary wave larger than this under the given circumstances. This is Malus's law. He says that we receive 8.5, and at this point we are receiving 5.7 watts per meter square. Okay, so he says to show the first step. How could we do that? We have I equals to I naught into cos square of theta. So I naught, which we introduced into the filter, is 8.5, and cos square of the angle is 35. Please be advised, always take the square first and then multiply this with 8.5. So let me show you this, how this is going to go. So cos of 35, calculate this first, simply take a square and then multiply this with 8.5. You get 5.7. Very straightforward, and we've successfully shown what we're supposed to show. So 5.7 watts per meter square is the intensity received on the outside or after the filter. Then he says, what is the value of angle alpha? Now this is going to be a difficult question, or you have to be clever about this. You see, now the wave is actually aligned along this plane. It was coming along this plane, but now it is oscillating like this. So it is already oscillating at an angle of 35 degrees in this plane or along this line. What have we done extra apart from 35? So 35 was already done. What have we done extra? How much filtration have we done so that it now comes out as 5.2? By my guess, this is going to be a very small number. This is going to be less than 35 at least. So let's calculate this. So what have we done to make 5.2? So I is equal to I naught cos square of theta. 5.2 is what I received. 5.7 is what we provided to the filter, and cos square of theta. So please don't forget to take the under root on the other side. So we find that the theta comes out as 17.2 degrees, which is a further increase of 17 from 35. You see, 35 was already done. How much more have we changed the angle? We have changed the angle to 17.2 degrees further at this point, so that now if we send 5.7, we get 5.2. So alpha, according to the diagram, is the complete angle from the starting point. So 35, what does this change? So 35 plus 17.2 gives me an answer of 52 degrees. So this is going to 52 degrees, right? Okay. The current in the lamp decreases. State and explain how the resistance may have changed. Very simple. If the lamp current has decreased, the temperature would have decreased. It would have reduced its heating effect. The temperature decreases and its resistance also decreases. And we know that for any conductor or a filament lamp, the temperature is proportional to its resistance. Higher the resistance, more energy it will transfer or convert as heat. It will start heating up. A cylindrical wire, okay, good. So has a resistance R. Total number of free electrons, charge carriers are given as N, and the elementary charge is E. The potential difference is V. He says determine the current, so no problem. And in the incoming parts, that is 1, 2, and 3, We're going to use these variables. This is what he's asking us to do. Okay, so don't try to force all these variables into a single part. Just wait for those parts to come in. So the first part is current, so that is going to be V equals to IR. So I is equal to V divided by R. Simple as that, V divided by R. The average drift speed or drift velocity, so we know the formula of current is equal to NAQV. Now the new changes are, this N is represented with capital N, cross-sectional area A as it is, and Q will be replaced by E, and V is the velocity. Okay, so since V is required by us, we're going to replace V in this situation. So V is equal to current divided by N, the charge density, multiplied by cross-sectional area, multiplied by the elementary charge E. Okay, now notice what has happened with E. Okay, so now, sorry, N. N is the number of electrons per unit volume. So this is actually going to be N divided by volume. And how to calculate the volume for a cylindrical wire? You see, if I observe a cylindrical wire like this, I can see that very clearly that this is the cross-sectional area as A, could be pi r square, no problem, but let's keep it as A. And this is its length or the respective length, whatever that may be. So if I want to find out the volume, I'll have to multiply A, the cross-sectional area, multiply by the length. The same ideology applies for this volume of a cylinder, which is actually pi r square H. Notice what's actually the similarity. Okay, all right. So this N is actually per unit volume with AL, right? So what do we come down to? What is going to happen? So this A gets cancelled out with that one. This A cancels with this one. L goes to the upper side, so we are left with IL divided by capital N into E. Now let's replace I as V over R. So I replaced by V over R becomes L divided by NE. This becomes VL divided by RNE. So this is your final answer. So VL divided by NRE. The average time taken for the electron to move the full length, no problem in this. The formula is speed is equal to distance over time. We have calculated the speed to be the velocity, okay, which is this part has already been calculated. Now he says the full length of the wire. So this will actually be, D will be changed as L, and speed, velocity will be changed as VL divided by NRE equals to L divided by T. Since he wants us to find time, let's first cancel out the variables to make it simple. L gets cancelled out and we have to find T. So T gets cross multiplied. We get T is equal to NRE divided by V. A simple reciprocal of this equation. So NRE divided by V will be our time taken. We move to the next question, which is related to Kirchhoff laws somehow. But this particular question is from Wheatstone bridge and the null galvanometer method. No problem. He says, what's the voltage of the 1800 ohm resistor? We can use the potential divider rule to quickly solve this. This will be 1800 divided by 1800 plus 1200. The voltage shared between them is 9 volts. That is of the source. This comes out as 5.4 volts. So this is 5.4 volts. Now notice that the electron entering at this junction had 9 volts. 1800 ohms consumed 5.4 volts. The remaining 3.6 volts show up at this junction, which will be consumed by this resistor, and the left electron that is going to go back to the battery is actually at 0 volts. So that is what goes back at this point is 0 volts, and the one actually coming out is actually 9 volts. Of course, we are assuming that the wires are behaving ideally and they are not consuming any voltage, but this is the non-ideal case. Okay. He says that this is a circuit that is presented and the galvanometer reads 0. That means this is the balancing point. And again, please be advised, this is actually the Wheatstone bridge concept. Wheatstone bridge concept, and now it has been replaced in your syllabus as the null method. But no need to worry, we're going to discuss this in detail and clear out any misconceptions that you might have. Okay, all right. So he says that it reads 0. First, let's do the discussion at this point. What's happening at this point? You see, let's replace this XZ as a resistor. Let's say if this was a resistor, and let's say there is a resistor over here as well. why is the ammeter reading no current? Why is the ammeter showing a zero value? Because what has happened? You see, the LDR consumes 5.4 volts, leaves only 3.6 volts at this junction. The current entering had a voltage of 9 volts, and at this point it is 0 volts. So 3.6 volts are being consumed by the 1200, right? So what is happening? So that means that if this is 3.6 volt, or this junction is at 3.6 volts, this junction must also be at 3.6 volts, because when there is no potential difference, there will be no flow of current. Okay. What does that mean? It means that these resistors are exactly the same, but we can't be so sure about it. You see, the problem is that I can't guarantee that this would be 1800 ohms. It's not possible. A wire does not have this much resistance, but the ratio will be the same. What do we mean by the ratio? Ratio means that the ratio between 1800 and 1200 will exactly be the same, the ratio between RZY and RXZ. However much voltage is being consumed by this piece of wire will be 5.4 volts, and however much voltage is consumed by this piece of wire will be 3.6 volts. So there will be a ratio amongst each other which is going to be equal to the ratio of 1800 and 1200. This is what the Wheatstone bridge concept was all about. That the product of opposite branches, what is the product of opposite branches? This branch and this branch will have the product of these two opposite branches will be exactly the same as the product of the other branches. Let me show you how it's going to go. So resistance of ZY multiplied by 1800, opposite branch resistance, is equal to the product of this branch, which is going to be equal to RXZ multiplied by 1200. And if you want to find out the ratio, then that will become RZY divided by RXZ equals to 1200 divided by 1800. So what have we come down to? We've come down to this idea that the ratio of resistances on the opposite branch are equal to the ratio on the other side as well, right? Okay. Now let's see how it's going to go. Okay. So calculate the length XZ along the resistance wire. No problem. I know how much voltage it is going to consume. The XZ part is supposed to consume 5.4. Why? Because I need this guarantee that when a 9 volt electron enters this point, when it leaves this junction, when it leaves or reaches point Z, it needs to have only 3.6, because 3.6 is at the center. If it has 3.6, only then there will be no flow of current through the branch, because the potential difference or the voltage difference will be 0. So I have this guarantee. Okay. So the length XZ divided by the length of the whole conductor, length XY, is being multiplied with 9 volts, okay, is equal to, or is going to be found, this is basically the length XZ, okay, is going to be equal to 5.4 volts. You see what we've done over here? We're applying the potential divider in some sense. You see, the whole wire consumes 9 volt enters and 0 volt leaves. The whole wire consumes 9 volt. What portion of this wire should consume 5.4 volts? What length should consume this? So this is that ratio that we are implementing over here. Okay, this whole length is actually given as 1.2 meters. When you algebraically solve this, this comes out as 0.72 meters. So this is 0.72 meters. Let's go back to the question. What does that mean? It means that 0.72 meters length is at this point, at the balancing point. Okay, this is 0.72 meters, and this is the remaining. Subtract this from 1.2 and you'll find a 0.48 meters. Okay, and this is what I told you before. The ratio is same. You see, the ratios are same. This is at a higher length, this is a smaller length, this is a higher value, this is a smaller value. Their ratios came out to be same because we want to compare the electron that left them. You see, 9 volt electron enters, leaves with only 3.6 volts after passing through 0.72 meters of this length of wire. Okay, all right. He says what's going to be the change in the intensity if something goes wrong. So The change is that the intensity decreases. So we know that the resistance of LDR is inversely proportional to light. If the light is decreasing, he says that the resistance is decreasing, then the light would have increased. So intensity of light has increased. It may have been placed into a sunny or sunny side area, or direct sunlight, could be anything. The total power produced is going to increase. Why is it going to increase? Because you see, the formula for power is P equals to I square R. If you reduce the resistance, right, the current increases. Now, although you may argue that since both of them are being multiplied, algebraically speaking, mathematically speaking, if you multiply one number that is increasing with a number that is decreasing, the effect should remain constant. Effectively, it should remain constant. It should not matter. You're right, but there is a problem. The problem is that I is being squared. So I is increasing at the rate of twice as much as this is decreasing. So the overall effect is going to increase. So although in terms of the formula for P equals to I square R, R is decreasing mathematically, but I is increasing at such a faster rate because it is being squared that P feels like that it is increasing overall. And where is this I and R? If you go back to the circuit, this is that I, the current generated by the battery. Why is it increasing? Because the overall resistance of this branch is decreasing. So even if you were to find out the overall resistance with 1 over R plus 1 over R, because this branch and this branch are in parallel, one branch loses resistance because the LDR is probably at 1000 ohms right now. The whole resistance of the circuit falls down and the current will increase from the battery. Okay, all right. The length xz, so the galvanometer reads 0. Now this is tricky. He says, what will happen if the LDR's resistance decreases? You see, as I've discussed before, that the ratio of these resistances, even after solving, came out to be same, right? Now, if the resistance of the LDR has decreased, that means that the balance point will change. Most definitely it will change. You see, now, if the resistance of LDR decreases, then it will take away less voltage. So if let's say 9 volt enters, it's possible that now it's only consuming 4 volts. It is consuming 4 volts for itself, leaving behind 5 volts for the next resistor. You can take any arbitrary example of assumed voltage, no problem. So what will happen? Is the wire experiencing any change in resistance? No, wire has a constant resistance along its length. Nothing is changing. So what will happen? You see, previously the electron entered at this point, and after covering a distance of 0.72, it would give a voltage of 3.6. And we know that if we allow this electron to flow and flow and flow, at the end it has 0 volts. So it means that as it moves along the line, it loses voltage, it loses electrical energy. Since the resistance has decreased and now I want to show a lower voltage, I will move this point back to this point so that this electron travels a smaller length of wire, resistance proportional to length. Smaller length of wire, smaller resistance, and smaller voltage will show up. So when you move this point from this point to this point, up to this point, it will probably now lose only 4 volts and come to this point. So now again, both points are at the same voltage. The galvanometer will reset its value to 0. There is no potential difference now. Okay, I hope that we understand that why this reads as decreases or move towards the left. Radioactivity is a very straightforward question. Everything is supposed to be memorized in this chapter. So he says P and Q are also same elements. Nucleus Q is unstable. So Q breaks down to form nucleus R plus with a beta particle with 0 minus 1. Now he tells you what are the number of protons in terms of isotopes. So isotopes have same protons. Number of neutrons are different or dissimilar. He says the change in quark composition. You see, this will have, and again, this is coming from memory. Okay, that what happens is that a proton, right? I believe so. Yeah. So a neutron changes to a proton. So neutron is 1 0. This is 1 1, and this is B minus 1 0. Okay. I believe so. I think. Yeah. So what happens with the quark composition, you have to memorize this, is that this is going to be up, down, down, and this converts into up, up, down. So what has happened in the quark composition? One down has changed into up. Okay. And then we have what is going to be extra with the beta particle. We know neutrinos are extra. So electron anti-neutrino will be ejected with the beta particle, beta radiation. Hadrons have 3 quarks always. And he says that there are 2 charm and one bottom quark. That is okay, fine. So he says what is the elementary charge in terms of E? No problem. Now 2 charms have +2/3 elementary charge, then +2/3 elementary charge, charm 1, charm 2, and bottom quark is actually -1/3e. This comes out as 1e or +1e. You can do this with a calculator as well if you're unsure about this. Use this 2/3 equals +2/3 equals minus fraction 1/3. Calculate this, you get 1. So this is your 1 elementary charge.